I mean, in field theory, one way to interpolate was to use the dimension, and that was a perturbative.
I didn't hear what you said.
In field theory or statistical mechanics, one way to interpolate between the dimensions was to use dimensional regularization, and that was perturbative. Okay? There was another way, which was to play with the power of k in the propagator, okay? And that was analytic regularization, okay?
Yeah.
Which you could fix the dimension, and then if you wanted to go away from perturbative to analytic things, it was perfectly well posed problem, because, well, can one do such a thing in
in a sense that's what we're doing, in a sense. We doctoring Fourier space in such a way that the volume element is k to some power. It's not the propagator, and we have the advantage that we still have equations of motion we can write, and we can put them on a computer.
No, can't you sort of just, well, maybe something goes evidently wrong, but just put some power of k in the dissipative term. I mean, in the
no. That, of course, that's a game I have played ad nauseam, and that would not give us anything.
I didn't understand.
I mean, that is what I have called many years ago modified dissipivity, and some people call it hypo viscosity.
No, not in viscosity, but in the convective term.
In the V grad V, yes.
Yeah.
If you do that, you'll be in big trouble with energy conservation.
Don't you break the linear invariance also?
You'll break
Galilei and everything break.
You'll break everything. I mean, you'll read trouble.
Hear it probably.
No, you don't break the linear. You don't break the linear invariance here, right?
No, of course, I break nothing.
You don't break?
No.
Only conservation.
And actually, it is in physical space. If you look at the solution, they don't even look anything fractal or something. In physical space, in Fourier space, they do.
Just a question.
My suggestion would rather be to try to use this trick on some non-turbulence problem and see what comes out. I mean, yesterday we discussed issue of where this is likely to help, maybe on dynamical critical phenomena, on KDZ, and so on.
I'm sure we've tried to do the numerical simulation at 4/3. Very slow, and then if you wait enough, you see something, or what do you think?
If you wait long enough, it goes towards something, but it's very slow. The flux goes to zero. So you start from initial condition, flux is zero. What do you do? You have to wait.
Wait, you work with forcing, with pumping. So you what with flux zero? You just hit it?
No. There's a delicate problem of interchange of limits. First of all, if you inject, you have to specify if you're injecting into living modes or dead modes, because anything that you inject in dead modes doesn't count. So you can, for example, I mean that's what Anna did. She carefully adjusted the injection rate so that the amount of energy injected in truly dynamical modes stays the same. But what happens is that in the real world with real computers and finite size, etc., it is very hard to prevent a significant fraction of this energy from going the wrong way. If you were able to let the Reynolds number at the same time to become higher and higher, you would be. But you can't do that with a finite resolution. And therefore, what is happening is that instead of having all the energy injected going to the left, you have less and less of it that goes to the left, and more that gets dissipated basically where it's injected. it doesn't matter too much to get the Kolmogorov constant, because the Kolmogorov constant you can recover from the energy spectrum and the amount of flux that goes there. But if you were doing the theoretical problem, where you don't have to worry about resolution, where you inject at a fixed rate, then everything would go to the left, and the flux would still be exactly what you inject in the inverse cascade. And the only thing as you approach 4/3 is that the spectrum goes higher and higher and higher. Of course, you have to wait until this is filled.
I don't think it will be so. I can tell you what happens when we in wave turbulence. And in wave turbulence, you change a parameter and Kolmogorov spectrum cross equilibrium. We know what happens analytically. It's a relation which we can solve, and numerically we can check that it works. The true solution in case of forcing, there is always equilibrium. Equilibrium exists. Now, when you have forcing, the true solution is this power law modified by logarithmic function. And this logarithmic function is a slow function, which means that scaling-wise, it's like equilibrium, but it's not equilibrium because it's multiplied by a logarithmic type function, which provides for a phase. It's not fine. This logarithm is a large number, but it's fine. It's a logarithm of
I'm not taking issue with that. I'm saying not at 4/3, but as you approach 4/3, there's still a finite distance from it, then you get the inverse cascade with a power law k minus 5 spectrum, which is higher and higher.
Also, but Luca asked about exactly for
exactly at 4/3 you can get a logarithm. Yes.
Yuri, I have
But it's
question.
absolutely fine.
Can I ask question?
Yeah.
So, did you try to do simulation for d less than
No.
4/3?
No, I mean, we have a theoretical prediction, of course. The theoretical prediction is that because you see, the flux is negative as long as d is greater than 4/3. Then it vanishes linearly with d minus 4/3, so it becomes positive again. Well, I don't know, in dimension. With a positive flux, you can't get an inverse cascade. The only possibility would be a direct cascade. But such a direct cascade of energy would be in conflict with entropy conservation. Therefore, the prediction is that the thing just
Yuri, I also
grows indefinitely, that you don't reach any steady state.
I think you do reach steady state.
I mean?
I think you do reach. I have different prediction, also based on wave turbulence. Okay, the different prediction, you actually get a spectrum which is an inertial range will be close to thermodynamic equipartition, slightly modified by the flux going on background of it.
Logarithmically.
It depends. I mean, in the middle of inertial range, it's not even logarithmic. It's Katz-Kantarovich direction.
That's conceivable. Actually, on my next visit to the Weizmann Institute, we intend to investigate numerically what's happening in dimension 4/3 and close to it, just below. We shall see. It can also be done by closure, of course, which is not so different from doing it by your favorite methods.
All right, thank you very much.